Welcome back. This is your host, Mr. Tarab, and we're going to continue by looking at conservation of momentum. The momentum of an object is given by its mass times its velocity, so it is a vector. It does not have its own units, so the units are kilogram times meter per second, or also Newton seconds. You can do some unit conversions to see why it works out that way. But the key idea of Newton seconds is that if you apply a force for a certain amount of time, as opposed to when we were looking at energy when you were applying a force for a certain distance, if you apply a force for a certain amount of time, that is also conserved for the system, because for the time that you're applying the force from object A to object B, then object B is applying an equal and opposite force to object A. And that force times time being applied is called impulse. And you can also read it from, let's say, a force over time diagram. It would be the area under the curve. Probably the best way to think about impulse is the same way we think about work. So we see work as the capacity to change the energy of something, and then you see the impulse as a change in the momentum. So again, work changes the energy, impulse changes the momentum. So it's pretty typical, for example, for a model rocket engine to tell you what the impulse is that it can provide. And the reason impulse can be a good analytic technique is that sometimes, such as in the case of a collision, which is what we're going to be looking at in a little bit more detail, the force that is applied is really high over a very small time interval. So it's not really useful to think about the force and the time separately, but it's better to think about the product of the two together. Again, a very high force for a very small amount of time, but the product of the two is going to be a finite quantity that we can work with. And so when two objects crash into each other and undergo a collision, momentum is conserved. In fact, this is true even if you crash into a wall, for example, because if you crash into the wall and the wall is attached to a planet, then that planet is going to move ever so slightly. So again, momentum is always conserved in a collision, but we're going to be looking at two types of collisions, one where momentum and energy is conserved, and one where momentum is conserved but energy is not, at least not mechanical energy. So we did discuss the conservation of energy last time, and I mentioned how that is a property of the fact that a force applied over a distance also has an equal and opposite reaction. But sometimes that force is acting on very small particles. For example, it's dissipating heat through moving molecules faster. And so sometimes such as when something, is undergoing friction, it's going to come to a stop. And even though the overall energy is conserved because it has dissipated the energy as heat, the mechanical energy is not conserved, because the object has not gained, for example, potential energy, and it's just come to a stop, so it's lost its kinetic energy. And this is the same thing that can happen if you have two objects that crash into each other and stick together. The energy associated with that after the collision, the mechanical energy, is actually lower than the sum of the two energies going into the collision. And so the inquiry problems will ask you to do two things. One of them is going to ask you to analyze an elastic collision, which is one where energy is conserved, where things bounce off each other. And one of them is going to ask you to analyze an inelastic collision, where the two objects stick together. So elastic collisions are actually more complicated mathematically, because you have two sets of equations. You have two sets of conditions that are being met. One is that momentum is conserved, and the other is that energy is conserved. So the way you would solve that is actually by setting up a system of equations, including quadratic equations, because the energy equations have a velocity squared in them, and so it gets pretty complicated pretty quickly. However, we're not going to ask you to do that for the problem you're solving. For the problem you're solving, which is question 3, we've already provided you the information of the velocity of one of the objects after the collision. And so you would basically solve it just using conservation of momentum. So you're going to take the original momentum of the two objects, and remembering again that velocity is a component of momentum, and therefore momentum is a vector. So if something is moving in the opposite direction, then that's going to subtract from the overall momentum. So pick an axis and stick with it. Again, your sign notation. So treat them as vectors, add them as vectors. That means you may need to subtract the numbers. And when you have the total momentum going in, then you know the momentum of the object whose velocity is given, and the rest of that momentum is going to be in the velocity of the, it's going to be in the object whose velocity is not given. And so you can use that to find the velocity of that object and its direction. Again, momentum is mass times velocity. For problem number 4, the objects stick together. And so essentially, you're going to take the overall momentum going into the collision, and now you know the mass of the overall object, which is one object stuck together at the end, and you can use that mass to find the velocity of the collided cars. Now, collisions are not always either perfectly elastic or perfectly inelastic. They could be somewhere in between and have a coefficient of restitution, it's called, somewhere between 0 and 1, depending on how close they are to a perfectly elastic collision with a coefficient of restitution of 1, or a perfectly inelastic collision with a coefficient of restitution of 0. In case you're wondering, you actually can have a coefficient of restitution greater than 1, and that involves an explosion where the mechanical energy after the collision, the kinetic energy, is higher than the kinetic energy going in. So for example, something like this. All right. And the last thing I want to mention about momentum is that all the analysis that I've talked about happens in one dimension. However, if you're interested in thinking about what happens in 2 dimensions, there's an interesting section in your book about that. And what we're talking about there is billiard balls. So, what happens, why is it that if you take one billiard ball that strikes a billiard ball that's not moving, then the 2 billiard balls will start moving at right angles from each other? So you can read more about that there if you're curious. The last thing I want to mention on that is you might notice in question number 3, it talks about ignoring the rotational energies associated with that. So there is some energy associated with the rotation. We looked at moment of inertia, and so if something is turning, it also has kinetic energy because of the way those particles are turning, and the kinetic energy associated with that is 1/2 I omega squared. We're not going to get into that in terms of the calculations, but it has some pretty interesting properties in terms of, for example, if you have a ball rolling down a ramp, it does not fall the same way that if you have an object sliding down the ramp. And lastly, question 5 is just a angular, or rather circular motion problem, so I'll let you figure that out on your own since it is basically review. Now that pretty much sums it up in terms of the assignments and what you need to do, but if you want to keep watching the video for a couple more minutes, I'll get into a couple things that we would have looked at if we had had a little bit more time in class. Again, not in much detail, but just wanted to let you guys know a little bit of what you might be missing. So first of all, there were topics that are outside classical mechanics that we would have gotten to at the end of the year, and we're not going to be looking at those. So that is everything dealing with electricity and everything dealing with earth science. So you'll be looking at electricity again if you take physics 2, and earth science stuff when you officially take that credit next year. So the last thing I want to talk about for a couple minutes is what we would have been looking, the only additional topic that we would have been looking at in terms of classical mechanics, which is Kepler's laws. And it tells us a little bit about sort of the nature of science. So Johann Kepler was a scientist who lived about 100 years before Newton, and he came up with descriptive laws for planetary motion. Again, he didn't say why those things were moving the way they did, like Newton did, but he basically just described the way that these things moved. And the way that he came up with these laws was he had a lot of data from Tycho Brahe, who was an astronomer from that time period, and he used Tycho's data to come up with general laws for the motion of the planets. So there had been a lot of discussion prior to this time about whether planets moved around the sun or whether the sun and the planets moved around the Earth. But the entire discussion, the way Copernicus had set it up, was that the orbits were circular. And the data just didn't quite line up with that. And so one of the things that Kepler realized was that the orbits, rather than being circular, were actually elliptical. So an ellipse is kind of like an elongated circle. Its definition is that there are two foci instead of one center, and if you take any point on the ellipse, the sum of the distance to the two foci is the same, rather than a circle where the distance between any point and the center is the same. And it turns out that one of the foci of the ellipse is the star that it revolves about. Now, the second law talks about equal areas being swept in equal time. And so you should probably go try to find a picture of this. Again, there's lots of resources on this online if you search for Kepler's laws. But the way that I like to think about it is, let's say you have a ball that's sort of riding along the crust of a pizza. And the equal areas being swept in equal time, the equal areas are the amount of pizza that's sort of being swept by the ball that's rolling along the edge. Now, this may seem rather trivial as to a circle, right? If you're going around a circle and you're going at a constant speed, then you're going to be sweeping equal areas in equal time. But it's actually not trivial when it comes to an ellipse, and when the distance between the planet and the star changes. And so what ends up happening is that it still sweeps equal areas, because when it's closer to the planet, but to the star, it actually moves faster. And when it's farther away, it moves slower. And that's kind of an interesting tidbit. And it actually means that a certain quantity called angular momentum about the star is conserved. And so the same way we looked at angular velocity and angular acceleration, there's actually a thing called angular momentum. And it happens to be conserved about the star as the planet is moving around, which means that any force acting on the planet cannot create a torque about the star, and therefore it must be pointed directly at the star. So what could it be, this force that's directed at the star? Well, of course it's gravity, and that's what Newton came up with. And the third law of Kepler deals with the orbital radius, or the semi-major axis in an ellipse, and how it's proportional to the orbital period as follows. So the square of the orbital period is proportional to the cube of the semi-major axis, or the orbital radius in a circle. And so that equation, you can manipulate a bunch of variables, and you can actually derive that from universal gravitation and from circular motion. And so basically what that means is that when Newton came up with his law of gravitation and his general understanding of physics and momentum and all those concepts, it matched Kepler's description of how the planets moved. He just sort of gave it a reason. So that maybe gives us some insight into how science is developed sometimes. You have certain observations, and then you develop a theory that matches those observations, and then you test it with other observations. So again, there's much more you can read up on that, but I just wanted to sort of give you a brief overview of it. That about sums it up. It's a shame that our year has sort of come to a close a little bit too soon. All right, I'm going to try to keep this video under the 15-minute YouTube time limit, but I want to wish you all the best. Take advantage of all the resources, and I look forward to reading through all your work. Thanks. Bye.